Chapter 15, Part 5 of Volume 2 of Airplane Flying Handbook, FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook by the FAA. Chapter 15, Part 5. Jet airplane approach and landing. Landing requirements. The FAA landing field length requirements for jet airplanes are specified in 14 CFR Part 25. It defines the minimum field length and therefore minimum margins that can be scheduled. The regulation describes the landing profile as the distance required from a point 50 feet above the runway threshold through the flare to touchdown and then stopping using the maximum stopping capability on a dry runway surface. The actual demonstrated distance is increased by 67% and published in the FAA-approved Airplane Flight Manual as the FAR Dry Runway Landing Distance. See Figure 15-22. For wet runways, the FAR Dry Runway Distance is increased by an additional 15%. Thus, the minimum dry runway field length will be 1.67 times the actual minimum air and ground distance needed, and the wet runway minimum landing field length will be 1.92 times the minimum dry air and ground distance needed. Certified landing field length requirements are computed for the stop made with speed brakes deployed and maximum wheel braking. Reverse thrust is not used in establishing the certified FAR landing distances. However, reversers should definitely be used in service. Landing speeds. As in the takeoff planning, there are certain speeds that must be taken into consideration during any landings in a jet airplane. The speeds are as follows. VSO, stall speed in the landing configuration. VREF, 1.3 times the stall speed in the landing configuration. Approach climb, the speed which guarantees adequate performance in a go-around situation with an inoperative engine. The airplane's weight must be limited so that a twin-engine airplane will have a 2.1% climb gradient capability. The approach climb gradient requirements for 3 and 4 engine airplanes are 2.4% and 2.7%, respectively. These criteria are based on an airplane configured with approach flaps, landing gear up, and takeoff thrust available from the operative engines. Landing climb, the speed which guarantees adequate performance in arresting the descent and making a go-around from the final stages of landing with the airplane in a full landing configuration and maximum takeoff power available on all engines. The appropriate speeds should be pre-computed prior to every landing and posted where they are visible to both pilots. The VREF speed, or threshold speed, is used as a reference speed throughout the traffic pattern. For example, downwind leg, VREF, plus 20 knots. Base leg, VREF, plus 10 knots. Final approach, VREF, plus 5 knots. 50 feet over threshold, VREF. The approach and landing sequence in a jet airplane should be accomplished in accordance with an approach and landing profile developed for the particular airplane. See Figure 15-23. Significant differences. A safe approach in any type of airplane culminates in a particular position, speed, and height over the runway threshold. That final flight condition is the target window at which the entire approach aims. Propeller-powered airplanes are able to approach that target from wider angles, greater speed differentials, and a larger variety of glide path angles. Jet airplanes are not as responsive to power and course corrections, so the final approach must be more stable, more deliberate, more constant, in order to reach the window accurately. The transitioning pilot must understand that, in spite of their impressive performance capabilities, there are 6 ways in which a jet airplane is worse than a piston engine airplane in making an approach and in correcting errors on the approach. The absence of propeller slipstream and producing immediate extra lift at constant airspeed. There is no such thing as salvaging a misjudged glide path with a sudden burst of immediate available power. Added lift can only be achieved by accelerating the airframe. Not only must the pilot wait for added power, but even when the engines do respond, added lift will only be available when the airframe has responded with speed. The absence of the propeller slipstream in significantly lowering the power on stall speed. There's virtually no difference between power on and power off stall speed. It is not possible in a jet airplane to jam the thrust levers forward to avoid a stall. Poor acceleration response in a jet engine from low RPM. This characteristic requires that the approach be flown in a high-drag, high-power configuration so that sufficient power will be available quickly if needed. The increased momentum of the jet airplane making sudden changes in the flight path impossible. Jet airplanes are consistently heavier than comparable-sized propeller airplanes. The jet airplane, therefore, will require more indicated airspeed during the final approach due to a wing design that is optimized for higher speeds. These 2 factors combine to produce higher momentum for the jet airplane. Since force is required to overcome momentum for speed changes or course corrections, the jet will be far less responsive than the propeller airplane and require careful planning and stable conditions throughout the approach. The lack of speed stability being an inducement to a low-speed condition. The drag curve for many jet airplanes is much flatter than for propeller airplanes, so speed changes do not produce nearly as much drag change. Further, jet thrust remains nearly constant with small speed changes. The result is far less speed stability. When the speed does increase or decrease, there is little tendency for the jet airplane to reacquire the original speed. The pilot, therefore, must remain alert to the necessity of making speed adjustments and then make them aggressively in order to remain on speed. Drag increasing faster than lift producing a high sink rate at low speeds. Jet airplane wings typically have a large increase in drag in the approach configuration. When a sink rate does develop, the only immediate remedy is to increase pitch attitude, angle of attack. Because drag increases faster than lift, that pitch change will rapidly contribute to an even greater sink rate, unless a significant amount of power is aggressively applied. These flying characteristics of jet airplanes make a stabilized approach an absolute necessity. The stabilized approach. The performance charts and the limitations contained in the FAA-approved airplane flight manual are predicated on momentum values that result from programmed speeds and weights. Runway length limitations assume an exact 50-foot threshold height at an exact speed of 1.3 times VSO. That window is critical and is a prime reason for the stabilized approach. Performance figures also assume that once through the target threshold window, the airplane will touch down in a target touchdown zone approximately 1,000 feet down the runway, after which maximum stopping capability will be used. There are 5 basic elements to a stabilized approach. The airplane should be in the landing configuration early in the approach. The landing gear should be down, landing flaps selected, trim set, and fuel balanced. Ensuring that these tasks are completed will help keep the number of variables to a minimum during the final approach. The airplane should be on profile before descending below 1,000 feet. Configuration, trim, speed, and glide path should be at or near the optimum parameters early in the approach to avoid distractions and conflicts as the airplane nears the threshold window. An optimum glide path angle of 2.5 degrees to 3 degrees should be established and maintained. Indicated airspeed should be within 10 knots of the target airspeed. There are strong relationships between trim, speed, and power in most jet airplanes, and it is important to stabilize the speed in order to minimize those other variables. The optimum descent rate should be 500 to 700 feet per minute. The descent rate should not be allowed to exceed 1,000 feet per minute at any time during the approach. The engine speed should be at an RPM that allows best response when and if a rapid power increase is needed. Every approach should be evaluated at 500 feet. In a typical jet airplane, this is approximately 1 minute from touchdown. If the approach is not stabilized at that height, a go-around should be initiated. See Figure 15-24 on the next page. Approach speed. On final approach, the airspeed is controlled with power. Any speed diversion from V, REF, on final approach must be detected immediately and corrected. With experience, the pilot will be able to detect the very first tendency of an increasing or decreasing airspeed trend, which normally can be corrected with a small adjustment in thrust. The pilot must be attentive to poor speed stability leading to a low speed condition with its attendant risk of high drag increasing the sink rate. Remember that with an increasing sink rate, an apparently normal pitch attitude is no guarantee of normal angle of attack value. If an increasing sink rate is detected, it must be countered by increasing the angle of attack and simultaneously increasing thrust to counter the extra drag. The degree of correction required will depend on how much the sink rate needs to be reduced. For small amounts, smooth and gentle, almost anticipatory corrections will be sufficient. For large sink rates, drastic corrective measures may be required that, even if successful, would destabilize the approach. A common error in the performance of approaches in jet airplanes is excess approach speed. Excess approach speed carried through the threshold window and onto the runway will increase the minimum stopping distance required by 20 to 30 feet per knot of excess speed for a dry runway and 40 to 50 feet for a wet runway. Worse yet, the excess speed will increase the chances of an extended flare, which will increase the distance to touchdown by approximately 250 feet for each excess knot in speed. Proper speed control on final approach is of primary importance. The pilot must anticipate the need for speed adjustments so that only small adjustments are required. It is essential that the airplane arrive at the approach threshold window exactly on speed. Glide path control. On final approach, at a constant airspeed, the glide path angle and rate of descent is controlled with pitch attitude and elevator. The optimum glide path angle is 2.5 degrees to 3 degrees whether or not an electronic glide path reference is being used. On visual approaches, pilots may have a tendency to make flat approaches. A flat approach, however, will increase landing distance and should be avoided. For example, an approach angle of 2 degrees instead of a recommended 3 degree will add 500 feet to landing distance. The more common error is excessive height over the threshold. This could be the result of an unstable approach or stable but high approach. It may also occur during an instrument approach where the missed approach point is close to or at the runway threshold. Regardless of cause, excessive height over the threshold will most likely result in a touchdown beyond the normal aiming point. An extra 50 feet of height over the threshold will add approximately 1,000 feet to the landing distance. It is essential that the airplane arrive at the approach threshold window exactly on altitude, 50 feet above the runway. The flare. The flare reduces the approach rate of descent to a more acceptable rate for touchdown. Unlike light airplanes, a jet airplane must be flown onto the runway rather than held off the surface as speed dissipates. A jet airplane is aerodynamically clean even in the landing configuration, and its engines still produce residual thrust at idle RPM. Holding it off during the flare in an attempt to make a smooth landing will greatly increase landing distance. A firm landing is normal and desirable. A firm landing does not mean a hard landing, but rather a deliberate or positive landing. For most airports, the airplane will pass over the end of the runway with landing gear 30 to 45 feet above the surface, depending on the landing flap setting and the location of the touchdown zone. It will take 5 to 7 seconds from the time the airplane passes the end of the runway until touchdown. The flare is initiated by increasing the pitch attitude just enough to reduce the sink rate to 100 to 200 feet per minute when landing gear is approximately 15 feet above the runway surface. In most jet airplanes, this will require a pitch attitude increase of only 1 degree to 3 degrees. The thrust is smoothly reduced to idle as the flare progresses. The normal speed bleed-off during the time between passing the end of the runway and touchdown is 5 knots. Most of the decrease occurs during the flare when thrust is reduced. If the flare is extended, held off, while additional speed is bled off, hundreds or even thousands of feet of runway may be used up. See Figure 15-25. The extended flare will also result in additional pitch attitude, which may lead to a tail strike. It is therefore essential to fly the airplane onto the runway at the target touchdown point, even if speed is excessive. A deliberate touchdown should be planned and practiced on every flight. A positive touchdown will help prevent an extended flare. Pilots must learn the flare characteristics of each model of airplane they fly. The visual reference cues observed from each cockpit are different because the window geometry and visibility are different. The geometric relationship between the pilot's eye and the landing gear will be different for each make and model. It is essential that the flare maneuver be initiated at the proper height, not too high and not too low. Beginning the flare too high or reducing the thrust too early may result in the airplane floating beyond the target touchdown point, or may include a rapid pitch-up as the pilot attempts to prevent a high sink rate touchdown. This can lead to a tail strike. The flare that is initiated too late may result in a hard touchdown. Proper thrust management through the flare is also important. In many jet airplanes, the engines produce a noticeable effect on the pitch trim when the thrust setting is changed. A rapid change in the thrust settings requires a quick elevator response. If the thrust levers are moved to idle too quickly during the flare, the pilot must make rapid changes in pitch control. If the thrust levers are moved more slowly, the elevator input can be more easily coordinated. Touchdown and rollout. A proper approach and flare positions the airplane to touchdown in the touchdown target zone, which is usually about 1,000 feet beyond the runway threshold. Once the main wheels have contacted the runway, the pilot must maintain directional control and initiate the stopping process. The stop must be made on the runway that remains in front of the airplane. The runway distance available to stop is longest if the touchdown was on target. The energy to be dissipated is least if there is no excess speed. The stop that begins with a touchdown that is on the numbers will be the easiest stop to make for any set of conditions. At the point of touchdown, the airplane represents a very large mass that is moving at a relatively high speed. The large total energy must be dissipated by the brakes, the aerodynamic drag, and the thrust reversers. The nose wheel should be flown onto the ground immediately after touchdown because the jet airplane decelerates poorly when held in a nose-high attitude. Placing the nose wheel tires on the ground will assist in maintaining directional control. Also, lowering the nose gear decreases the wing angle of attack, decreasing the lift, placing more load on the tires, thereby increasing tire-to-ground friction. Landing distance charts for jet airplanes assume that the nose wheel is lowered onto the runway within 4 seconds of touchdown. There are only 3 forces available for stopping the airplane. They are wheel braking, reverse thrust, and aerodynamic braking. Of the three, the brakes are the most effective and therefore the most important stopping force for most landings. When the runway is very slippery, reverse thrust and drag may be the dominant forces. Both reverse thrust and aerodynamic drag are most effective at high speeds. Neither is affected by runway surface condition. Brakes, on the other hand, are most effective at low speed. The landing rollout distance will depend on the touchdown speed and what forces are applied and when they are applied. The pilot controls the what and when factors, but the maximum braking force may be limited by tire-to-ground friction. The pilot should begin braking as soon after touchdown and wheel spin up as possible, and to smoothly continue the braking until stopped or a safe taxi speed is reached. However, caution should be used if the airplane is not equipped with a functioning anti-skid system. In such a case, heavy braking can cause the wheels to lock and the tires to skid. Both directional control and braking utilize tire-ground friction. They share the maximum friction force the tires can provide. Increasing either will subtract from the other. Understanding tire-ground friction, how runway contamination affects it, and how to use the friction available to maximum advantage is important to a jet pilot. Spoilers should be deployed immediately after touchdown because they are most effective at high speed. Timely deployment of spoilers will increase drag by 50 to 60%, but more importantly, they will spoil much of the lift the wing is creating, thereby causing more of the weight of the airplane to be loaded onto the wheels. The spoilers increase wheel loading by as much as 200% in the landing flap configuration. This increases the tire ground friction force, making the maximum tire braking and cornering forces available. Like spoilers, thrust reversers are most effective at high speeds and should be deployed quickly after touchdown. However, the pilot should not command significant reverse thrust until the nose wheel is on the ground. Otherwise, the reversers might be deployed asymmetrically, resulting in an uncontrollable yaw towards the side on which the most reverse thrust is being developed, in which case the pilot will need whatever nose wheel steering is available to maintain directional control. End Chapter 15, Part 5. Recording by Dale Latham. End of Volume 2 of Airplane Flying Handbook FAA-H-8083-3A by Federal Aviation Administration.